Okay, so this is a video outlining how to derive differential equations from circuits. What you will see is this is actually not that much different from the way you derived standard equations for resistor networks. The only thing that's going to change is the expressions that you will use in order to derive these differential equations. I'm going to go over it fairly briefly in a very systematic way, and hopefully this will help you kind of get an idea as to how you actually go about deriving differential equations from circuits. Okay, so we will be looking at circuits with different kinds of elements than we have in the past, and in particular we're going to be looking at circuit elements with capacitors and inductors. And so to do that, we have to know what the voltage to current relationships are for these types of elements, and in particular for the resistor, we had that the voltage drop was equal to the current through the resistor times the resistance. For the capacitance, actually, we have that the current flowing through that capacitor is actually dependent on the rate of change of the capacitor voltage times its capacitance. And for the inductor, we have that the voltage across the inductor is actually dependent on the inductance times the rate of change of the current across the inductor. And believe it or not, this is the only thing that's going to change when it comes to capacitors, inductors, and resistors. Now, I can rewrite this relationship by integrating both sides of the equation and dividing by the capacitance, so that I'm going to get 1 over c, the integral from negative infinity to t, of ICs of t, and that will be equal to VCs of t. So I can also invert these relationships to get them in terms of current or voltage and vice versa, and I can do the same thing for the voltage across the inductor. So I'm going to divide by L and integrate, so I have 1 over L from negative infinity to t. The voltage across the inductor, tau, d tau, there should be a d tau here and a tau, which is equal to I L's of t. So in order to derive equations for circuits, we're going to actually use these relationships. And then for the resistor, it would be IR equals V's of R, so T over R. We're going to use these relationships, and we're still going to apply KCL, and we're still going to apply KVL. They still apply. There's one caveat where typically when we analyze these circuits, we're going to solve for VL, for VC or IL. You will notice that you will rarely be asked to solve for VR or for IC or for VL. And the reason for that is that VC and IL actually sit under a derivative. And so we know these things have to be continuous. Because if VC is not continuous, then its derivative is not defined, which means that its current is not defined. And for a circuit, for it to be physical, the current has to be defined. Same thing for the voltage. And so IL and VC will always be continuous. And so as a result, when we derive differential equations in terms of them, we can ensure that our solutions will be continuous. And later when we look at switch circuits, this will become more important. For now, it's just a minor detail. Okay, so like I said, we're just basically going to use our relationships that allow us to go from voltages to currents, and our relationships that allow us to go from currents to voltages, in order to apply KVL and KCL and solve for circuits in the same way that we've been dealing with resistor networks. So just to give you an example, for this particular circuit, we would still have that if we put in a source here, VI, we would have that VI equals VR plus VL plus VC. So basically, the input voltage has to be equal to the sum of the voltage drops. In the next slide, we're actually going to derive a differential equation for the capacitor voltage of this circuit, or sorry, for the inductor current or the current of this circuit in terms of by using this KVL. And then in the other slide, we're actually going to derive the equation for this particular circuit, or an equation for this particular circuit. Okay, so let's look at this particular circuit here. What we have is, if we apply KVL, we're going to have that Vn of t minus, so Vn is the voltage from here to here, and then we're going to have the voltage drop across Vr, so minus Vr of t, which is the voltage drop across the resistor, minus the voltage drop across the inductor, minus the voltage drop across the capacitor, have to sum up to 0. So that's basically saying that VR, VL, that the voltage Vn has to be equal to the sum of the voltage drops across the 3 elements. So of course, there are 4 unknowns in this equation, and or 3 unknowns in this equation, and we don't know them all. So the first thing I can do here is just basically move VR, VL, and VC to the other side, so that I get that the input voltage of t, which would be my forcing function, is equal to VR of t plus VL of t plus VC of t. Now, in this particular circuit, the same current that flows through the resistor is the same current that flows through the inductor, which is the same current that flows through the capacitor. And so we actually want to write each of these 3 things in terms of the current. And so what we can do is use this table here, which gives us the voltage to current relationships. And so we're going to get that actually this is just equal to R times the current I of t, plus, for the inductor we have L dIL dt, so L ddt of I of t. And then for the capacitor we have 1 over C, the integral from negative infinity to t I of t, d tau, or sorry, dt. Now, of course, you might be wondering, okay, we have an integral in this equation, and how do we get rid of it? In general, after you use this table to derive your equation, you end up with an integral, what you're going to do is just take the derivative of both sides of the equation. So what you're going to get is that the derivative of the input is equal to R times the derivative of the current plus L. When you take the derivative of a first order, then you get a second order derivative. And then you're going to get 1 over C I of t. So the derivative will effectively cancel out that integral. And that's it. You just derived the differential equation for this. So as you noticed, we're just going to apply KVL or KCL, and then we can use our voltage to current relations or current to voltage relations in order to get our equation for the circuit. So we looked at the series example. Let's look at one that has things in parallel to get a better idea of how to do this. Okay, so in this particular case, KCL would tells us that IR, IL, and then you have kind of IC, which is the voltage drop across all of those 3. That's going to be equal to IN. So we have that IN of t. So if I apply KCL on this node, it's equal to IR of t plus ILs of t plus ICs of t. And then in this particular case, what's common to all of them is the voltage across the capacitor. So we actually want to write everything in terms of those voltages. So here we have the voltage across the resistor divided by R. So we have VC divided by R. That's equal to the current of the resistor plus for an inductor, we have that the current is actually 1 over L, the integral from negative infinity to t, V Cs of t, or the voltage across the inductor, which is Vc, and then this should be tau d tau. And then for the capacitor, we have that the current is related to the voltage by a derivative, so C d dt of Vcs of t. And at this point, again, we have an integral, so to get rid of it, we just simply take the derivative of both sides of the equation. And so we're going to get that this is actually equal to the derivative of in of t is 1 over r d dt of Vcs of t plus 1 over L. The derivative cancels out the integral, so we're just left with Vcs of t plus C d dt squared Vcs of t. So yeah, it's that simple. We just derived the differential equation for this particular circuit. Okay, so let's look at one last example before I conclude this video. Okay, so this one's a little bit more complicated because, as you can see, what we have here is we have a inductor current and a capacitor current, and we have kind of a node here, a node here. And so what we're going to have, if we look at this equation here, we have a current IL coming in, and then we have a current IR going through here, and then we have a current IC going through here. So one equation is that IL has to be equal to, so ILs of t equals IRs of t plus ICs of t. Additionally, we have here the voltage across the inductor, VL, minus, so that's the voltage from here to here. So if I do this loop, and then the voltage from here to here is just Vc. So we're going to have that Vin of t equals, what is it? VLs of t plus Vcs of t. So we get this from K VL, so KVL, and we got this from KCL. Okay, so at this point, this is a little bit more complicated because, as you can see, we have choices. So let's just assume that we're only interested in solving for the voltage across the capacitor. So what that means is that we want to write this VL in terms of the voltage across the capacitor, or we want to write this equation here in terms of the voltage across the capacitor. So let's just go ahead and write everything in terms of voltages just to simplify things. So I'm going to take this equation, and then I'm going to go ahead and figure out how to write everything in terms of all the currents in terms of voltages. And we have basically that IL is just going to be equal to, IL is just equal to 1 over L VL over, so basically we're going to rewrite this. So this is just 1 over L, the integral from negative infinity to tau, V tau, VL tau, d tau, is equal to, what did we have in the next slide? Okay, so the next one is IR, which is just Vcs of t divided by the resistance, because that's the voltage across the resistor, and then plus IC, which is just C d dt of Vcs of t. So at this point, in order to get an equation that doesn't have BL, we can take the derivative of both sides. So we basically are going to get VL of t on the left-hand side, and then we're going to get ddt Vcs of t, 1 over r, plus C d dt squared Vc sub t. Now, at this point, it's kind of simple to solve this because what you can see here is that we have a function, we have a way to represent VL in terms of the voltage across the capacitor. And so what I can actually do here is just to this equation add Vc sub t, so that I get that this is equal to Vn sub t. And then I'm going to add Vc sub t. And now that gives me my differential equation. So as you can see here, we're still going to apply KCL and KVL. And once we've decided which quantity we want to solve for, then we can derive a differential equation that that effectively is in terms of that quantity that we want to solve for. Okay, so I just solved for VC, but let's just say I wanted to actually solve for IL instead of VC. So that would make things a little bit more complicated. But let's see what we can do. So I'm gonna go ahead and delete all this. So we want to actually solve for IL now instead of VC. Okay, so let me just try to. So because we want to solve for IL, we actually want to figure out how to get rid of. We want to figure out how to write IC and IR in terms of IL. And so we're just going to go ahead and try to write this equation in terms of I. Okay, so let's try to write this equation in terms of I. So what we're going to have here is, well, Vn sub t equals L d dt of IL sub t plus, and then what we're going to have here is the Vc is actually equal to this, but the current going through the capacitor, IC, is actually equal to IR. Sorry, it's equal to IL minus IR, because remember that whatever comes in through here has to be split between these two. So this equation tells me that, node equation tells me that the current IC is equal to IL minus IR. So I'm going to have basically 1 over C, the integral from negative infinity to t of ILs of tau minus IRs of tau d tau. Okay, so at this point we need to get rid of the integral, so we take the derivative of both sides of the equation. So we're going to take the derivative. This becomes a square. This all goes away. And it becomes t and t. Okay, so at this point, of course, we have a problem because we have IL here, but now we have IR. So we need to figure out how to get rid of that IR. And to get rid of that IR, we have to remember that IR is just really the voltage across the capacitor divided by R. And what is the voltage across the capacitor? IR is just the voltage across the capacitor divided by R. So let's just go ahead and plug that in. Minus VL. Yeah, so here we can actually go ahead and plug that in. So here I'm just going to go ahead and plug that in. So we have that this is just the voltage across the capacitor divided by R, but you know this is actually equal to V in minus VL, and so we can just plug that in instead, and then write this in terms of IL. So we're going to have minus V in minus VL divided by R, and then VL is just equal to L dIL dt, if you remember, L d dt of IL. So as you can see now, we can just move that V in over R to the other side of the equation, and now we have an equation in terms of IL. So this was a little bit more complicated. That being said, all you needed to do was apply standard KCL and KVL, and then the thing that changed is that now you have all these derivative expressions in your circuit. So now that we know how to derive these differential equations, and in the previous slide we learned how to solve them, in the previous lecture we learned how to solve them, in our lecture we're actually going to look at the solution to a lot of these circuits. We're going to solve a lot of these circuits, and we're going to look at how these solutions look.